Hey everyone, today we're going to be talking about algebraic proofs. So, what is a proof? A proof is when you justify something to be true, right? Like if your parent asks you, did you turn in your assignments? Show me proof, right? So you show that the grade has been changed and there's like justification like, hey, this means that I have done my assignments, right? So there's a way to justify something is true, right? And in a way that it's convincing and it's irrefutable, right? You can't say otherwise. So there's a ton of kinds of proofs. There's paragraph proofs, there's two-table proofs, there's all kinds of proofs. We're going to be focusing on two-sided table proofs, where we are solving some algebra problem here on the left. We're going to be solving algebra problems on the left, and then we are justifying on the right. And all this means is that when we're justifying, we are presenting an example or a reason for why that algebra step is correct. We're not going to be focusing on geometric proofs or anything higher than that, but hopefully this algebraic proof is a good introduction to what is to come in your future life in math. So, how do we justify proofs? Well, we have to talk about equality properties and talk about how the meaning behind them and how they're justified. So here we have, if you look at the list, we have a ton of properties: the addition property, multiplication, all the way down to distributive property. Some of these I'm sure you've seen before, maybe you just didn't know the name of, right? We talked about this in the list. I gave you a list of class in class that you can use as well. But all these properties are properties that are true for real numbers. When I'm solving an equation, I'm allowed to do this because of these properties. And these properties that you learned in Algebra 1. So the first thing that we're going to be able to do is I'm going to give you some examples, and we just want to justify what is the name of the property being applied. After that, once we can recognize what properties are being applied, we can then go about solving a problem and justifying each step using these properties. All right, let's get right to it. So here we have state the property that justifies each statement. In the first example, we have if angle A, saved by the bell, if angle A equals measure angle A, then measure angle A equals 80. Right? All we're doing here is we're swapping the order. 80 equals A, therefore A equals 80. And that is true, right? If x equals 5, then 5 equals x. When you're just switching the order because of the property of equality, right? This is just equality. We're talking about this is a symmetric property of equality. A symmetric property of equality says you can switch the order. The next one, if Rs equals Tu and Tu equals Yp, then Rs equals Yp. So all this is saying is that if a segment equals another segment and that same segment equals another, the first one must equal the last one. Okay? I can say that this must equal this because they're connected through Tu. That's what the conclusion is about. We call that the transitive property. When you have three objects that all mean the same and are connected by something, then the first object or the first person or the first something is connected to the last one. This is very similar to the transitive property of, this is called the transitive property. This is very similar to the law of syllogism, right? The way we did the law of syllogism in class was P implies Q, or if you look at one of my other videos, and Q implies R, we can then say P implies R. It's very, very similar. So we call this a transitive property. A transitive property of equality, where we connect the first one to the last one, just like we did here with P implies R. The next step. Here, if you look at it, we have 7x equals 28. What do we need to do from here to get to x equals 4? Well, you need to divide 7 on both sides. All right? And if you divide by 7, you get x equals 4. What did we do? We did division. This is called the division property of equality. In the next example, we have VR plus TY equals EN plus TY. Therefore, VR equals EN. What is missing when you go from here to here? Notice how these TYs are gone. So VR equals EN because we're able to remove the TY. So in order to remove it, we have to subtract TY on both sides. And if we're subtracting, we're left with VR equals EN. This is a subtraction property. I know this might seem counterintuitive because you're looking at this sign and you're like, well, we're adding on both sides. Wouldn't that be the addition property of equality? It's like, yes, it would be if that were your conclusion. But you're starting with this and you're getting to them being gone, right? You're trying to justify the step. What happened from the beginning to the end? If the end had addition on both sides, then it would have been addition. But since the end removes this, the conclusion means we had to subtract in order to get to this end. I hope that makes sense and it clarifies things. If not, leave a comment below. I can justify it and maybe explain it a little bit better for you. This last one says if measure of angle 1 equals 30 and angle 1 equals angle 2, then angle 2 equals 30. So the way to think about this is I look at the first one. What is the difference between where you start to where you end? The difference here of where you start to where you end is that we were able to replace the 1 with the 2. Why did we replace the 1 with the 2? Well, because they're equal. Since they're equal, I can substitute in here the value or the number 2 because they're congruent, they're the same. So if something equals something else and you're replacing it with an equal value, you can just change the name of it. Right? You can just change the name of it. Like with me. I'm Mr. Lopez. I also go by Rudy. I also go by Papa because I'm a dad. And so at home, you can replace my name with Papa, Rudy. At school, you can replace my name with Mr. Lopez. I used to be a coach, so you could replace that name with coach. So whenever something is equivalent to something else, you can replace it with something else, and it means the same thing. Same thing here. You're replacing angle 1 with angle 2 because angle 1 is the same as angle 2. We call this substitution. Maybe you have a nickname that you go by, and your name can be replaced with that nickname because they mean the same thing. All right, so here we're just justifying different statements. Let's go ahead and do some actual algebraic proofs. So we'll start with a very generic example. Here we have solve for x. Now, whenever you're doing an algebraic proof, I'm going to make a two-way table here so I can explain it. Whenever you're doing an algebraic proof, what we're saying here is we're trying to justify each step. At the very end, we're going to have our answer. You're given a scenario, you're given a situation. We're going to call that our given. That's always going to be given, the first step. We're now trying to solve for x and justify the meaning behind it and why we got what we got. So all you really have to think about is how would you solve this problem? I would start by multiplying distributive property. When you distribute, you get negative 2x minus 6 minus 2x equals 54. What did we do to get from the first step to the second? We distributed. So we just write distributive property. That's my justification. That's my proof that I can go from one step to another. Now, we're not done, but if you justify each step with a property that we spoke about in the very beginning of this video or in the notes in class, then you'll be able to see how every step is justified until you get to the very last step where x equals something. Now, what would we do? Well, we would combine like terms. We have negative 2x and negative 2x. That gives you negative 4x. What do we call this step, this combining like terms step? Well, what's really happening here is you're combining this value. Let me change colors for a second. this value and this value, you're combining them and you're replacing it with an equal value. So instead of saying negative 2x minus 2x, you can replace that by saying negative 4x because they mean the same thing. When you replace something of equal value with something else, we call that substitution. Right? Now, if I wanted to solve for x, I'm trying to get rid of that 6. So I'm going to add 6 to both sides. So I have negative 4x minus 6. I'm going to add 6 on the left, and I have 54, and I'm going to add 6 on the right as well. By adding 6's on both sides, right, what are we doing here? We're trying to cancel the 6's on the left. If we're adding on both sides, we call this the addition property. This is called the addition property of equality. Now, if I start simplifying, right, like I said earlier, the 6's will cancel. You're left with negative 4x. And then on the right, 54 plus 6 is the same as saying 60. So since we're replacing 54 plus 6 with something smaller or something of equal value, right, that replacing, that simplifying, we call that substitution. Because 54 plus 6 is the same thing as saying 60. You're not changing the value, you're just replacing it with something different. Now, lastly, what do you do to solve for x? Since you're multiplying times 4x, you divide by negative 4 on both sides. And this step of dividing on both sides, sorry, let me just write it again over here so I can see that the problem is separate. What I would do is I would divide by 4 on both sides. And by dividing on both sides, right, this step is called division property. Division property of equality. And then finally, we're going to start simplifying and leave x on its own. X equals negative 15. What happens here? Well, these cancel to 1. We were able to replace this fraction, 60 divided by negative 4. Instead of writing it as a fraction, we can write it as a whole number without changing its value, so we call this substitution. The reason why this is called a proof is because we just showed how this problem equals negative 15. X equals negative 15. That is an algebraic proof. And I was able to prove it by justifying every single statement along the way. Because every single statement was proven to be correct, I can conclude that x must equal negative 15. And there's no other option. It's 100% correct. This is an algebraic proof, a two-table algebraic proof, where you solve the problem on the left and you justify on the right. And if you can justify every single thing, then the last step, the proof part, must be correct. Now, you might see it like this too. You might see the two-table proof where it's already solved for you, partly or maybe partly explained, right? You're given a scenario, 8x minus 5 equals 2x plus 1. Prove that x equals 1. I'm trying to prove that x equals 1. Well, you can follow the proof on the left and the right and try to fill in the blanks, or you can just solve it yourself. I like to do that. I like to solve the problem myself and then write the steps on the left. Now, the very first step, I'm always going to write it as a given. And I'm going to try to solve this over here. I'm going to put this in black. I'm not going to try to solve it. I'm going to solve it. 8x minus 5 equals 2x plus 1. So the first thing I want to do is I want to combine the x's in the same side. So I'm going to subtract 2x on both sides. Think about what you just said, right? I'm going to subtract 2x on both sides. That's called subtraction. Then what happens when I subtract 2x on both sides? Well, I have 8x and negative 2x. I combine like terms, right? I'm left with 6x minus 5 equals, this cancels, 1. Since I replaced this with this, we called that substitution. Hence, the step here being used is substitution property. So I just write down my step here on letter C. This is what I'm left with. After that, I combine like terms. I can just copy that down over here. 6x minus 5. Now what do I do to solve for x? I move the 5 over, so I add 5 to both sides. Sorry, I'm trying to write this in red so that I don't confuse the blue with the red, right? The side work. So I move 5 to the other side by adding 5 to both sides, right? Since I added 5 on both sides, I'm just going to show it over here that I did that. I have 6x minus 5 plus 5 on the left, and then the right has 1 plus 5 on the right. Notice how it says there's an addition property. We did that. We did addition. The next step is to simplify and combine like terms. So we have 6x the 5's cancel, and you're left with 6. We're replacing these numbers with another thing that's equivalent, right? 6x equals 6. What did we do? We combined like terms, or we did substitution. Substitution property. We replace 1 plus 5 with 6. Finally, we're going to want to divide both sides by 6. I keep messing up the color, sorry. When you divide both sides by 6, what did we just do? Division. And that's what we're justifying here on the left. See how the problem over here on the left is very, very similar to what I am doing? But as I'm doing it, I'm thinking out loud, and I'm saying, okay, what did I just do? I did this, I did this, I did this. And then for the very last step, we simplify, right? The 6's are going to cancel. You're left with x equals 1. We can replace a fraction with something equivalent, smaller, easier to look at. We're left with x equals 1, which is a substitution. I like to use substitution or think of it as simplifying or combining like terms, because that's all you're really doing, right? 6 divided by 6 is the same as 1. You're simplifying it. And we're done. We proved that the original problem, x equals 1. The proof will always be at the very bottom, the part that you solve, and then the statements that you use to solve it, to justify it, are right on the right. All right, guys, I hope this has helped. Please let me know if I can help you with anything else. Don't forget to like, subscribe, and I will always calculate later.